Welcome to Spring LIB.
Hi everyone, so what we have here is a problem that involves a package that has an initial velocity at a of 8 feet per second and a mass or weight of 5 pounds. We know that theta 1, which is the angular displacement from A to C, is 30 degrees, and from A to B is 45 degrees. We know that the initial slope that the particle starts at has an angle of 45 degrees with respect to the horizontal. What we're asked to solve for is the speed of the package when it reaches point C and when it reaches point B, and we're also asked to find the normal force of the package at point C. This problem will involve us using Newton's second law and also our knowledge of normal and tangential motion. So what we can do first is go ahead and draw the free body diagram of our package on the inclined ramp. So here's our package. As you can see, we have a normal force that is coming from the incline. We also have a weight force that is acting on the center of mass. And what we can do is actually define two angles, theta and phi. Phi is going to be our angle of initial incline. So as from the problem statement, we can see that phi is equal to 45 degrees. And our angle theta is the angle that's changing as we move from A to C to B. So the way that we can define this is we can say that the angle to the center to the angle to the ground will be theta, and the angle with respect to the horizontal will be phi, and that's equal to 45 degrees. So this will help us as we move from different thetas along the motion while we're still on that slope angle of 45 degrees. So what we can do first is sum up our forces in the tangential direction. Now, from using our free body diagram shown above, we can see that our total net force in the tangential direction, which is given by Newton's second law, is equal to 5 times cos phi, which is simply the weight component in the phi direction, in the direction of acceleration, times the mass, which is 5 over 32.2 times at. What this gives us is a tangential acceleration equal to 32.2 cosine of phi. Next, what we can do is do Newton's second law in the normal direction. We can say that the net force in the normal direction is equal to m times an, and we'll see that this is equal to the normal force from the ramp minus the weight force in this direction, and that's equal to mv squared over r. So we can do 5 divided by 32 over 2 v squared over r, which is given to us as 20 feet. Next, what we can do is we can use the differential expression that v dv is equal to a tangential times ds. What we can do is plug in for at here and say that the integral of v dv is equal to the integral of 32.2 cos phi times ds, which is going to be 20 times d phi, because that's just a differential arc length. So we take this integral from 45 degrees to phi, and this integral from v1 to v. What this gives us is 1/2 v squared minus 1/2 vi squared, which we know to be 8 feet per second, so that's going to be 8 squared, which is equal to 64.4 sine phi minus sine of 45, and that's in brackets. Now what we can do is that we can say at a phi of equal to 45 plus 30 degrees, so that's phi is equal to 45 plus 30 degrees. This takes us to our point C, so this gives us a phi that's equal to 75 degrees. This gives us a VC, so we'll solve for that V here, this gives us a VC equal to 19.9 feet per second. Now we can use our value of V and plug it in for our expression for n, which is given by n is equal to 5 divided by 32.2 times v squared over 20 plus 5 sine phi. Now recall that our phi is just 75 degrees. This gives us a normal force equal to 7.91 pounds. So that's another part of our answer. We can actually go ahead and box this answer as well. And to solve for the velocity at B. So at B, we can see that our phi is just going to be equal to 45 plus 45 degrees. So at phi equal to 90 degrees, this gives us a velocity that's equal to 21 feet per second. And that's our final answer.